Welcome to our deep dive into thermochemistry. Students often run into trouble figuring out how to handle different types of heat calculations, so we are going to tackle a wide variety of them in this series. We'll be looking at how to find the heat of a reaction using heat of formation, heat of combustion, bond energies, and atomization energies. We'll also explore heats of precipitation, neutralization, displacement, solution, and even touch on lattice energy and energy level diagrams.
Let's start with our first major type of calculation, finding the heat of a chemical reaction when you are given the heats of formation for the compounds involved. Now, when we say heat of a chemical reaction, that's actually a broad umbrella term. The specific name depends entirely on the type of reaction taking place. If the reaction is a combustion reaction, we are finding the heat of combustion. If it's a hydrogenation reaction, we are finding the heat of hydrogenation.
Most of these thermochemistry calculations rely on Hess's law to solve them. To make things easier to digest, we are going to divide our approach to Hess's law into two distinct methods. The first method is by calculation, where we use a specific algebraic formula. The second method is using Hess's cycles, which involves drawing out visual energy diagrams.
Let's look at the first method, by calculation. To find the standard heat of any given reaction, we use a specific formula. We take the sum of the heats of formation of all our products, and from that, we subtract the sum of the heats of formation of all our reactants. It's a straightforward plug-and-play algebraic method. Let's apply this to an example question. Here we have the combustion of a liquid organic compound, ethanol, reacting with oxygen gas to yield carbon dioxide and water. Based on our formula, our products are carbon dioxide and water, so we will sum their heats of formation first, and then subtract the heats of formation of our reactants, ethanol and oxygen. Before we start plugging numbers into our formula, there is a crucial rule you must keep in mind. The enthalpies of formation for all elements in their standard normal physical states are always zero. In our current reaction, oxygen is an element in its standard gaseous state, so its heat of formation will simply be zero. Now, let's set up our calculation. We must look at the stoichiometric coefficients from our balanced equation. We have 2 moles of carbon dioxide and 3 moles of water for our products. For our reactants, we have 1 mole of ethanol and 3 moles of oxygen. We multiply the heat of formation for each substance by these exact coefficients. Next, we dive in and substitute the given values. The heat of formation for carbon dioxide is negative 393, so we multiply that by 2. We add that to 3 times the value for water, which is negative 286. Then we subtract the reactant side, 1 times negative 275 for the ethanol, plus 3 times 0 for the oxygen. When we punch all of that into our calculator, we get a final answer of negative 1369 kilojoules per mole. But this number isn't just a value. It has a physical bearing that we can comment on. For heats of reaction, the sign indicates whether the reaction is feasible or spontaneous. Because our heat of reaction is highly negative, it tells us this reaction is highly exothermic, feasible, and spontaneous. Now let's look at our second method for solving these problems, Hess's cycles. You might see these referred to by a few different names depending on your examiner. They are also called enthalpy cycles or thermochemical cycles. Sometimes, examiners even incorporate them under the name Born-Haber cycles, which were originally developed for ionic solids but are frequently extended to covalent compounds as well. When handling the heat of a reaction using given formation values, the structure of Hess's cycle follows a standard rule. Because formation values represent the creation of a compound from its base elements, all of our arrows in the cycle must point away from the constituent elements and towards the reactants and products we are forming. Let's transpose our previous combustion equation into a cycle. First, we need to check the compounds in our reaction and identify the base elements they are formed from. We have ethanol, carbon dioxide, and water. This means our constituent elements at the bottom of our cycle will be carbon as a solid, oxygen as a gas, and hydrogen as a gas. Next, we need to balance these elements against our main equation. Continuing with our analysis of the ethane reaction, we can visualize the enthalpy changes using a cycle. Because we cannot point arrows into an element, since elements are not formed, they are the starting point, we place our constituent elements at the bottom. From these elements, we draw arrows pointing upward to form our reactant, ethane, and our products, carbon dioxide and water. The enthalpy change that leads to the formation of these compounds is derived directly from their standard heat of formation values. When we calculate the final value, the easiest way to memorize the process is to look at the direction of the arrows. We add all the clockwise arrows together and equate them to the anti-clockwise arrows.
In our cycle, the heat of combustion plus the formation of ethane equals the total formation energy of the products. Making the heat of combustion the subject of our formula gives us negative 1,369 kilojoules per mole. Because this value is negative, the reaction is exothermic and energetically feasible.
Let us look at a second example. We are given a reaction between ammonia and fluorine gas to produce nitrogen trifluoride and ammonium fluoride. We can solve for the enthalpy change using two different methods. The first is by calculation using the standard formula. The enthalpy change of the reaction equals the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Notice that fluorine is an element in its standard state, so its heat of formation is exactly 0.
Now we simply punch in the values. For our products, we have 1 mole of nitrogen trifluoride at negative 114 and 3 moles of ammonium fluoride at negative 467. We add those together. Then we subtract the reactants, 4 moles of ammonia at negative 46 plus 0 for the fluorine. When we carefully run these numbers through the calculator, subtracting the negative reactant value, we arrive at an overall enthalpy change of negative 1,331 kilojoules per mole. The second method utilizes an enthalpy cycle. First, we must ensure our main equation is perfectly balanced. Then we identify the key elements that make up these compounds, nitrogen, hydrogen, and fluorine gases in their standard states. We place these elements at the bottom of our cycle. We then draw arrows pointing from these base elements up to our reactants and up to our products, because the compounds are formed from these elements. We do not point an arrow to the fluorine reactant, as it is already an element. By observing the cycle, we can see which arrows follow the same continuous path. The arrow forming the reactants and the arrow for the reaction itself flow in a clockwise direction, while the arrow forming the products flows anti-clockwise. Equating these pathways, we get the heat of reaction plus the formation energy of ammonia equaling the total formation energy of the products. Solving this algebraic expression yields the exact same result, negative 1,331 kilojoules per mole. Now we are moving into category 2. Previously, we calculated the heat of a reaction given formation values, but what if you were given combustion values instead? To find the heat of formation using combustion data, we will again employ two methods: algebraic calculation and enthalpy cycles. Let's dive into the first method using an example where we need to find the standard enthalpy of formation for propan-1-ol. Under the calculation method, our very first step is to extract the given data and write out the balanced combustion equations. Remember, enthalpy of combustion is strictly defined as burning 1 mole of a substance. So we write the combustion of 1 mole of propane-1-ol, yielding carbon dioxide and water, and label it equation 1. Then we do the same for carbon, labeling it equation 2, and for hydrogen, labeling it equation 3. We use fractional coefficients for oxygen if necessary to ensure we only burn exactly 1 mole of the fuel. Next, we must clearly define our required equation. The question asks for the formation of propan-1-ol. This means we write an equation where propan-1-ol is the single product, formed from its constituent elements in their normal physical states. We need solid carbon, hydrogen gas, and oxygen gas. Balancing this to yield exactly 1 mole of propan-1-ol requires 3 carbons, 4 hydrogens, and half a mole of oxygen gas. This is the target equation we are trying to build. Now we compare our required equation with our given data to see how we can manipulate the steps to match. We need 3 moles of carbon on the reactant side, so we multiply equation 3 by 4. We need 4 moles of hydrogen on the reactant side, so we multiply equation 3 by 4. Finally, our target has propan-1-ol on the product side, but equation 1 has it on the reactant side. To fix this, we reverse equation 1, which mathematically means we will subtract its enthalpy value. Finally, we substitute the standard heat values into our manipulated expression. We take 3 times the combustion of carbon, add 4 times the combustion of hydrogen, and subtract the combustion value of propan-1-ol. When we resolve the arithmetic, we find that the standard enthalpy of formation for propan-1-ol is negative 313 kilojoules per mole. This specific value has significant implications for the stability of the compound, which we will analyze as we continue. Picking up right where we left off, let's formalize how we calculate the heat of a reaction using bond energies. The formula is quite straightforward. The heat of reaction is equal to the sum of the bond energies of the bonds broken in the reactants minus the sum of the bond energies of the bonds formed in the products. Remember, breaking bonds always requires an input of energy, while forming new bonds releases energy. Let's look at an example, the combustion of gaseous ethanol.
First, we need to identify every single bond involved. In 1 molecule of ethanol, we have 1 carbon-carbon single bond, 4 carbon-hydrogen single bonds, and 1 carbon-oxygen double bond. We are reacting this with 2.5 moles of oxygen gas, so we have 2.5 oxygen-oxygen double bonds. On the product side, we form 2 molecules of carbon dioxide, which gives us 4 carbon-oxygen double bonds in total, and 2 molecules of water, giving us 4 oxygen-hydrogen single bonds.
Now we substitute the standard bond enthalpy values into our formula. We sum up the energies for the bonds broken, which gives us 3,980 kilojoules per mole. Then we sum the energies for the bonds formed, which totals 4,816 kilojoules per mole. Subtracting the bonds formed from the bonds broken gives us a final heat of reaction of negative 836 kilojoules per mole. Because this value is negative, it indicates an exothermic process, meaning the products are at a lower energy level than the reactants. This tells us the reaction is thermodynamically feasible.
Alternatively, we can visualize this using a Hess's law cycle, sometimes called an enthalpy cycle. We place our reactants and products at the top. The intermediate state at the bottom consists of completely separated gaseous atoms. The arrow pointing down from the reactants represents the energy required to break all the bonds. This is an endothermic step. The arrow pointing up from the gaseous atoms to the products represents the energy released when new bonds form. The overall heat of reaction is just the mathematical sum of these pathways.
Let's try a slightly more complex example, the combustion of liquid ethanol. There is a crucial detail here. Bond energies strictly apply to compounds in the gaseous state. Because our ethanol is a liquid, we cannot just start breaking bonds. We must first supply the heat of vaporization to convert liquid ethanol into gaseous ethanol. For this reaction, that's an additional positive 44 kilojoules per mole. Once it's a gas, we can tally up the bonds to break. 5 CH bonds, 1 CC bond, 1 CO bond, 1 OH bond, and 3 OO double bonds. Let's run the numbers. The sum of the bond energies for the bonds broken in gaseous ethanol and oxygen is 4,731 kilojoules per mole. We must add our 44 kilojoules per mole for vaporization, bringing the total energy required to 4,775. On the product side, forming 2 molecules of carbon dioxide and 3 molecules of water releases 5,750 kilojoules per mole. Subtracting the energy released from the energy required gives us a highly exothermic heat of combustion of negative 979 kilojoules per mole.
Before we move to our next calculation, we need to clarify the difference between bond dissociation energy and atomization energy. Bond dissociation energy is the energy needed to break a specific bond in 1 mole of a gaseous molecule. Atomization energy, however, is the energy required to form exactly 1 mole of gaseous atoms from an element in its standard state. If you are given the bond dissociation energy for a diatomic molecule, like hydrogen or chlorine, you must divide it by 2 to get the atomization energy, because breaking 1 mole uses 2 moles of atoms. Let's apply this to finding the enthalpy of formation for chloromethane. The balanced equation forms 1 mole of chloromethane gas from solid carbon, hydrogen gas, and chlorine gas. To use a Hess cycle, we first atomize all reactants. Solid carbon sublimes to gaseous carbon, requiring 715 kilojoules. We need 3 moles of hydrogen atoms, so we multiply the hydrogen bond dissociation energy of 435 by 1.5. We need 1 mole of chlorine atoms, so we multiply the chlorine bond dissociation energy of 248 by 0.5. Summing these gives us our total atomization energy. Setting up our cycle algebraically, the enthalpy of formation plus the energy released by forming the bonds in chloromethane equals the total atomization energy. Chloromethane has 3 carbon-hydrogen bonds and 1 carbon-chlorine bond. Plugging in those bond energies, the total bond formation energy is 1575 kilojoules. We subtract this from our total atomization energy of 1491.5, yielding an enthalpy of formation of negative 83.5 kilojoules per mole. The negative sign confirms chloromethane is stable because it is formed exothermically. We can also work backwards to find an unknown bond energy. Let's find the average phosphorus-chlorine bond energy in phosphorus trichloride. We are given the enthalpy of formation as negative 306 kilojoules per mole. First, we atomize the reactants. Atomizing solid phosphorus takes 314 kilojoules. For chlorine, we are given the atomization energy directly as 121 kilojoules per mole of atoms. Since our balanced equation requires 3 moles of chlorine atoms, we multiply 121 by 3, giving 363 kilojoules. Now we set up our equation. The enthalpy of formation equals the sum of the atomization energies minus the energy of the bonds formed. So negative 306 equals 677 minus 3 times the PCl bond energy. Rearranging the equation to solve for the unknown, we find that 3 PCl bonds equal 983 kilojoules. Dividing by 3 gives us an average bond energy of positive 327.67 kilojoules per mole. Remember, bond energies are always positive values because breaking bonds requires energy.
Now, let's shift gears to ionic solids and look at two ways to represent their thermochemistry: energy level diagrams and Born-Haber cycles. If a question specifically asks for an energy level diagram, you must draw a vertical energy axis. Arrows pointing up represent endothermic processes with positive energies, and arrows pointing down represent exothermic processes. A Born-Haber cycle, on the other hand, is a closed loop of reactions, where you simply equate the sum of the clockwise pathways to the sum of the anti-clockwise pathways.
Let's construct a Born-Haber cycle to find the lattice energy of copper-2 chloride. We start with the formation equation from solid copper and chlorine gas. To reach the lattice energy step, we must convert these standard elements into gaseous ions. We sublime the copper, then apply the first and second ionization energies to reach a copper 2+ gaseous ion. For chlorine, we atomize the gas to get 2 moles of chlorine atoms and then apply the first electron affinity. Crucially, because we have 2 moles of chlorine atoms, we must multiply the electron affinity value by 2.
Following the cycle, the enthalpy of formation is equal to the sum of all the atomization, ionization, and electron affinity steps plus the lattice energy. We plug in our values. Negative 220 equals the sum of our positive steps, which is 3,283, plus our negative electron affinity step of negative 728, plus the lattice energy. Solving for the unknown, we find the lattice energy is negative 2,775 kilojoules per mole. This large negative value represents the massive amount of energy released when these gaseous ions combine to form the solid crystal lattice. We can use this lattice energy to determine the enthalpy of solution for copper-2 chloride. The process of dissolving a salt involves 2 theoretical steps. First, breaking the solid lattice into gaseous ions, and second, hydrating those ions. Because we are breaking the lattice, we must reverse the sign of our lattice energy to positive 2775. We add this to the given hydration energy of negative 2883. The result is negative 108 kilojoules per mole. Because the overall enthalpy of solution is exothermic, it predicts that copper-2 chloride is a soluble salt. If you don't want to draw a cycle, you can achieve the exact same result using Hess's law by algebraic calculation. Our goal equation is gaseous copper-2+ ions and gaseous chloride ions forming solid copper-2 chloride. We simply take the standard equations provided and manipulate them to match our goal. We reverse the ionization and sublimation equations for copper, reverse the electron affinity and atomization equations for chlorine, and keep the formation equation as is. Summing these manipulated values yields the exact same lattice energy, negative 2,775 kilojoules per mole. Let's transition to a new type of calculation, enthalpy of neutralization. Consider an experiment where we mix 50 cubic centimeters of 1 molar nitric acid with 50 cubic centimeters of 2 molar potassium hydroxide. The first step in any calorimetry problem like this is to find the total volume of the reaction mixture, which is 100 cubic centimeters. Assuming the density of the solution is roughly that of water, 1 gram per cubic centimeter, we have a total solution mass of 100 grams. We will use this mass to calculate the heat absorbed by the solution. Let us determine the heat evolved during this neutralization reaction. We use the standard formula, Q equals mc delta T. The mass of our combined solution is 100 grams, the specific heat capacity is 4.2, and the temperature change is 13 degrees Celsius. Plugging these values into our calculator, we find that the heat evolved is 5,460 joules. Next, we need to find the number of moles of water produced because enthalpy of neutralization is defined per mole of water. First, we calculate the moles of sulfuric acid used, which gives us 0.05 moles. Since each molecule of sulfuric acid produces 2 hydrogen ions, we multiply by 2 to get 0.1 moles of hydrogen ions. The reaction ratio of hydrogen ions to water is 1:1, meaning exactly 0.1 moles of water are formed. Now we scale our heat value to represent exactly 1 mole of water. If the formation of 0.1 moles of water produces 5,460 joules, we divide that heat by 0.1. This gives us 54,600 joules for 1 mole. Because the temperature of the mixture rose, heat was given out, making this an exothermic reaction.
Therefore, we must add a negative sign, resulting in an enthalpy of neutralization of negative 54.6 kilojoules per mole. Moving on to the heat of displacement. Consider an example where excess magnesium powder is added to 50 cubic centimeters of 0.2 molar iron 2 sulfate. We must make a few standard assumptions here. We assume the density and specific heat capacity of the solution are the same as pure water. Crucially, even though solid magnesium is added, it is in excess, so the solution itself acts as the limiting reagent. We ignore the mass of the magnesium powder and calculate the mass of the solution simply as 50 grams. With the mass established, we calculate the temperature change. The temperature of the mixture rose from 30.5 degrees to 40.0 degrees, giving a change of 9.5 degrees Celsius. Using our heat formula, we multiply the 50-gram mass by 4.2 and by the 9.5 degree temperature change. This reveals that 1,995 joules of heat were evolved during the displacement. To find the enthalpy of displacement, we determine the moles of iron displaced. We calculate the moles of iron 2 ions in the original solution, which is 0.01 moles. Since magnesium displaces iron in a 1-to-1 ratio, exactly 0.01 moles of solid iron are formed. Dividing our heat of 1,995 joules by 0.01 moles gives us 199,500 joules. Adding our negative sign for the exothermic process, the enthalpy of displacement is negative 199.5 kilojoules per mole. Let us look at a final example, the heat of precipitation. Here, 50 cubic centimeters of 0.5 molar silver nitrate is added to 50 cubic centimeters of potassium chloride. The first step is to find the total volume of the mixture, which is 100 cubic centimeters. Using our standard assumption that the density is 1 gram per cubic centimeter, the total mass of the reacting solution is 100 grams. Because the two starting solutions were at different temperatures, we must first find their average initial temperature. Averaging 29.5 and 28.5 gives us exactly 29.0 degrees Celsius. The highest temperature reached was 32 degrees, meaning the temperature change is 3 degrees. Plugging this into our heat equation, 100 grams times 4.2 times 3 gives us 1,260 joules of heat evolved. To find the moles of the silver chloride precipitate formed, we write out the ionic equation. Silver ions react with chloride ions to form solid silver chloride. We calculate the moles of silver ions from the silver nitrate solution, yielding 0.025 moles. According to the 1-to-1 molar ratio in the balanced equation, the number of moles of the silver chloride precipitate formed is also 0.025. Finally, we scale the heat evolved to 1 mole of precipitate. If 0.025 moles of silver chloride produced 1,260 joules, we divide that heat by the number of moles. This yields 50,400 joules for 1 mole. Because heat was released into the surroundings, the enthalpy of precipitation is negative 50.4 kilojoules per mole. To wrap up our discussion on enthalpy calculations, remember these key takeaways. Always start by calculating the total heat evolved using Q equals mc delta T, making standard assumptions for aqueous solutions. Next, carefully identify your limiting reactant to find the exact moles involved. Enthalpy is simply that heat scaled to 1 mole. And finally, if the temperature of the solution rises, the reaction is exothermic, and your final enthalpy value must carry a negative sign.